We have a word problem. Ladder slides down a house at 3 feet per second. How fast is the angle changing when the foot of the ladder is 15 feet from the house? I suppose we need to put a note on here. Let's measure the angle. Measure angle from ground to ladder. Because there are two angles. Do you agree? There are two angles, so we better make sure we clarify it. Measure the angle from the ground to the ladder. All right? So the first question is, can we draw a situation for this problem? All right? I'll make this a little smaller. Make this a little smaller. All right. You have your house, right? And you have the ground. And you have your 25-foot ladder against the house. And it's sliding down the house at 3 feet per second. All right, you know this is a related rate because it's based on time. You have 3 feet per second. And it's asking, the key word here, so you know it's different than optimization, is how fast. How fast is the angle changing? And again, I said measure the angle from the ground to the ladder here. So we'll do that in purple. So there's the angle. So this is the sketch of the situation. And they want to know how fast that angle is changing when this distance right here is 15 feet. All right. That's kind of a sketch of the situation. We now have to break this into a shape we can use, right? And I want you to see a right triangle, right? That is the purpose of having a ladder. I want you to see the right triangle. And the question is which of these, and there's a lot of stuff happening here, right? We have 3 sides. We have 2 angles. And the question is, what things have to have variables? And I'll start with that. Obviously, since the angle's changing, that has to have a variable. Obviously, it's sliding down the house. So y has to have a variable. It's obviously, if it's sliding down, it has to be sliding out. So this has to have a variable. But the one leg that doesn't have to have one is a hypotenuse. That ladder is always 25 feet long as you slide down the house. We still know that this is going down, so we know dy dt, all right? Dy dt equals, and again, since this distance is getting smaller, since that is getting smaller, the big thing here is to realize this is a negative rate of change, negative 3 feet per second, okay? And what we want to find here, and I'll do it in blue, is we want to find d theta dt when x is 15 feet. That's our unknown. All right? So what we've done, we've made a sketch, we've developed the sketch into a actual math problem triangle, right? And now we have to write a formula. And here's the hardest part about these. There are a couple formulas that could be written. So let's try to write them all, and then we'll pick what we think is the easiest one. Because there's a whole bunch of relationships. Okay? Let's start with it. I could write sine of theta, right? And that's y over 25 feet. When we look at this triangle right up here, right? I suppose I could write cosine of theta equals x over 25 feet. All right? I'm getting a little lazy. I didn't write feet on the next one, right? And finally, I suppose I could write tangent of theta equals y over x. And we want to be aware now what we're looking for. We're looking for d theta dt. And that's going to come out, if I take the derivatives of these trigs, I'll get a d theta dt. I will, on all 3. All right? I know dy dt. I know dy dt. I don't know dx dt, everybody. So One of the things I think of then with this is I am not, for sure, I do not want to do this, right? That's going to be y and x. You'd have to use the quotient rule or bring up x and have a product rule. This is a poor choice. This is a poor choice. It'll work. It can be done. And then the next thing is I see that I know dy dt, and I won't have to calculate dx dt. So I'm going to get rid of this one. And I see that the relationship I want to use in this case is sine theta equals y over 25 feet. All right? And I'll actually save some space on this. I'll actually erase these. And everybody, I want to be clear. That's the equation. But when I start thinking about the derivative of this function, I really want to think of it this way. And maybe you saw it that way in your head, but I want to think of it this way. So I take the derivative of this function in red. Derivative of sine is cosine. D theta dt. The derivative of 1/25 feet y is 1/25 feet, y is 1, dy dt. All right. You start to think to yourself, oh, cool, y and x don't matter in this, right? Because there's no y in it anymore. So that looking at this point when x is 15 feet might not seem so important, but it's still going to be important, okay? So right away, I realize that there's no variables over here. And I know dy dt. So everything on the right side is a known. I know that I'm searching for d theta dt. That's my unknown. But I got a problem. I don't know the cosine theta ratio. I don't know cosine theta ratio. My big recommendation, especially for students taking the AP test in May, do not find the angle. Do not find the angle. Do not find the angle. This is a beautiful right triangle. You know you're looking when x was 15 feet. So I want to be clear. You know this. You're looking at the instant that this was 15 feet, and this was 25 feet still, and this is theta. I don't want to go through a lot of trigonometry, but every one of us at this point in calculus should be able to look at this blue triangle I just drew and say, hey, the cosine of that triangle is 15/25. Right? That's the ratio. Don't find the angle, because if you find the angle and then use your calculator, you're going to get a decimal, and you're not going to get 0.6 exactly. You're going to get like 0.59. You got the ratio, so we do that. So that's that. And you notice I didn't reduce it. I didn't reduce it. And then dy dt was -3 feet per second. And everyone, I guess I should be clear. I skipped a step here. On the cosine ratio right here, I suppose it was 15 feet over 25 feet, right? So both of those feet cancel. Both of those feet cancel. So I can show them there in green for an instant. But now, again, this is just how I operate. I see feet and feet. I get rid of those. I see that we have 25 on both the bottoms, so I can get rid of those. It's one term on both sides. And now I'll take the 15 feet on the left and divide it over to the right and get d theta dt equals -3/15. Okay? And I start to look at my units, and I'm left with no units on top and seconds on the bottom. But when you have no units, we typically write what? Radians, right? Because radians are a unitless thing. And that would make sense for this theta. So everyone, and again, we want to simplify that. -3/5 reduces to -1/5, right? Rads per second. I'll level with you guys. I'm not real great with radians in my head. I can't really picture how fast that's moving. Is everybody with me? How many? I can't picture in 1 second how fast the ladder is collapsing this angle when you tell me rads. So I might be tempted to convert radians if I want to see if this is right in my head. I know pi radians is 180 degrees. Everybody with me? So I might take my calculator here at this point a number here because it's just a little odd. So 180 divided by 5 pi. And guys, this is just close, okay? It's not exact, but this makes sense to me. I can picture this. It's changing approximately 11.5 degrees per second. Let's be clear. The answer is actually the black. The green is simply for the sake of argument, so I can picture how fast is that angle compressing. Okay? And that makes sense to me. I can see that. If you're moving 3 feet per second, and this was a 3, 4, 5 triangle, 15, you were still 20 feet in the air here. 3, 4, 5, right? Times 5. And it's moving 3 feet. You are falling fast. You are falling fast. And again, all these problems can be solved with other trig ratios. Straight up, you can solve this one with tangent. But you're going to have to find dx dt, and it's just a lot more work. Okay? Again, the key to related rates is just practicing, and it's always in the setup up here up top.